Good morning, student. Welcome to TYBSc Organic Chemistry Lecture Series. Myself, Dr. Kailas Labhade, Associate Professor and Head, Department of Chemistry, S.V.K.T College, Deolali Camp, Nasik. Student, during last few lecture, we have started rearrangement reaction, and this is the last lecture of rearrangement reaction. In this lecture, we are going to see three important rearrangement reaction. Let's see the recap of last lecture. During last lecture, we have seen pinacol-pinacolon rearrangement. We know that this rearrangement is acid catalyzed rearrangement of vicinal diol. In this rearrangement, pinacol is converted to pinacolon or diol is converted to aldehyde or ketone. In pinacol-pinacol rearrangement, migratory aptitude is very important. In pinacol-pinacol rearrangement, carbocation is formed, and that's why rearrangement is going to take place. Migratory aptitude is tertiary greater than secondary greater than primary. The loss of OH group, which produce more stable carbocation, is generally undergo protonation, and finally there is formation of aldehyde and or ketone as a product. During last lecture, we have seen Lossen rearrangement. Lossen rearrangement is orthoacyl derivative of hydroxamic acid on heating with a base produce corresponding isocyanate. This rearrangement is called as Lossen rearrangement. Isocyanate, when undergo hydrolysis, it is converted to corresponding primary amine. Hydroxamic acid is first converted to orthoacyl or orthosulfonyl derivative, and when it is treated with base or when it is heated, there is formation of isocyanate as an intermediate which on hydrolysis produces primary amine. During last lecture, we have also seen Schmidt rearrangement. Reaction of carboxylic acid or aldehyde or ketone with hydroxyic acid in presence of strong acid gives isocyanate or nitrillium ion as an intermediate. This intermediate on hydrolysis produce primary amide or amine. In Schmidt rearrangement, generally carboxylic acid, aldehyde or ketone, they are the starting material, and the final product is amine, amide or formamide derivative. Sometime when starting compound is aldehyde, alkyl cyanide is formed as a product. Now today we are going to see electrocyclic rearrangement, introduction, mechanism and example of few electrocyclic rearrangement. In that case, we are going to see Claisen rearrangement, we are going to see Cope rearrangement, and finally we are going to see Mc-Lafferty rearrangement. At the end of this session, students should able to write the mechanism of Claisen rearrangement, they should able to write the mechanism of Cope rearrangement, they should able to write the mechanism of Mc-Lafferty rearrangement. They should able to predict the product by using these rearrangement reactions, and students should able to apply their knowledge of these rearrangement reaction in organic synthesis. Students, let's start with electrocyclic rearrangement. Electrocyclic reaction is the type of pericyclic reaction where pi bond is converted to sigma bond or sigma bond is converted to pi bond. Electrocyclic rearrangement or electrocyclic reactions are either photochemical or thermal reaction, means they are catalyzed by photochemical way or thermal method is used as a catalyst. Either ring opening or ring closing is going to take place during electrocyclic rearrangement. Let's see in this example, this is cis trans diene. This is pi bond, this is another pi bond which is present in this diene system, and this is the starting compound of this reaction, that is cis 3,4-dimethyl cyclobutene is the substrate molecule. When this molecule is heated, there is movement of sigma as well as pi bond is taking place, and this product is formed, that is cis and trans diene. Similarly, when photochemical electrocyclic reaction is take place, ring opening is going to take place. There is movement of sigma bond as well as pi bond, and again trans diene is formed. Means when photochemical reaction is carried out, there is trans geometry of the double bond, and in this case there is cis trans geometry. Now Claisen rearrangement is the first electrocyclic rearrangement we are going to see. This rearrangement was discovered by Claisen in 1912. An allyl vinyl ether on heating undergo 3,3 sigmatropic rearrangement and produce gamma delta unsaturated carbonyl compound. This is called Claisen rearrangement reaction. Starting compound of this Claisen rearrangement reaction is allyl vinyl ether, and when this ether is heated, there is formation of gamma delta unsaturated carbonyl compound. The reaction is concerted process where all bond formation and bond breaking take place simultaneously. Now why it is called 3,3 sigmatropic rearrangement? Let's see in this diagram. If you denote this oxygen as 1, this carbon is second and this carbon is third. From this side, this is 1, 2, 3. There is bond formation between third carbon from this side as well as third carbon of this side. Hence it is called 3,3 sigmatropic rearrangement. Here the mechanism is shown how that bond movement is taking place. These pi electrons are shifted here, means this single bond is converted to double bond. This bonding electron pair, it is shifted here, means breaking of CO bond is taking place and there is formation of CO double bond, and this double bond is converted to single bond. This bonding pair of electron, it is utilized for formation of bond between this carbon and this carbon. Hence this is the product which is obtained in Claisen rearrangement reaction, and it is gamma delta. This is alpha carbon, this is beta carbon, this is gamma carbon, and this is delta carbon. Gamma delta unsaturated carbonyl compound is the product of Claisen rearrangement reaction. Now in Claisen rearrangement reaction, we have used the term allyl vinyl ether. For that purpose, we should know what is allyl and what is vinyl. Let's see. This is allylic position, means allylic carbon is the carbon atom attached to carbon-carbon double bond. This is the carbon-carbon double bond, and this is allylic carbon. If substituent is attached here, say for example if chlorine is attached to this carbon, then we can call that molecule as allyl chloride if chlorine is attached here. This is allyl chloride, and this carbon is called as allyl carbon. Listen again, allylic carbon is the carbon atom attached to carbon-carbon double bond. This is carbon-carbon double bond, and this is the carbon which is attached to carbon-carbon double bond. That's why this is allylic carbon. And if chlorine is attached to this allylic carbon, then we can get the compound allyl chloride. Now there is another term, that is vinylic position or vinyl chloride. This is vinyl chloride. Let's see, vinylic position or vinylic carbon is the carbon which involved in double bond with another carbon atom. Means this is vinyl carbon and this is another vinyl carbon. If chlorine atom is attached to this carbon, then it is called vinyl chloride. Means this carbon atom is called as vinyl carbon. This carbon is also called as vinyl carbon. And this is the vinylic chloride. This is vinyl chloride and this is vinylic chloride. Now why vinylic? Because this carbon is substituted by two groups. That's why it is vinylic chloride, and this is vinyl chloride. This is allyl vinyl ether. In this diagram it is shown This is allyl carbon and this is phenylic carbon, and in between that there is oxygen. That's why it is allyl vinyl ether. Now benzylic and phenylic position. This is benzylic position and this is called as benzyl chloride. Benzylic carbon is the carbon atom attached to benzene ring, and phenylic carbon means the carbon atom which is part of the benzene ring. This is phenylic carbon, and this is phenyl chloride, or you can call it as chlorobenzene. Now these are some features of Claisen rearrangement. The Claisen rearrangement is an exothermic reaction. It is concerted reaction, that is simultaneously bond breaking and bond formation is taking place, and it is pericyclic reaction, means there is movement of pi bond as well as sigma bond. This Claisen rearrangement involves 6-member transition state. We are going to see that transition state during next slide. There are substantial solvent effect, means if there is polar solvent that accelerate the rate of the reaction, and the solvent which able to form hydrogen bond, they give fast rate for this rearrangement reaction. Now let's see the example of Claisen rearrangement reaction. It is allyl vinyl ether. This is double bond. Next to this is allyl carbon, and this is vinyl, and that's why it is allyl vinyl ether. In this case there is aryl. Aryl group is substituted with that oxygen, and when this is heated, it undergo Claisen rearrangement, and the mechanism is shown in this structure. This is bonding electron pair which is present in pi bond of this benzene ring is utilized for the attack. It attack on this carbon atom. This pi electron are shifted on this carbon, and this bonding electron is shifted here. That's why there is breaking of carbon oxygen bond is take place. This is the product which is obtained in this case. It is alpha, beta, gamma, delta, means gamma delta unsaturated carbonyl compound is formed as a product. Now we can write its tautomers by movement of this hydrogen from this place to this place, and this is the tautomer of this, and it is the alcohol, as well as it contain C double bond C also. Now let's see here. In this case, position 2. If you term this carbon as carbon number 1, this is carbon number 2. This is 3, 4, 5 and 6. In this case, position 2 and 6, they are blocked. Means already substituents are present. R2 is present as well as R1 is present. Now in this case, when this Claisen rearrangement is take place, first of all this group is attached to this carbon. Say for example it is second carbon, and after that again rearrangement is take place and there is formation of para substituted product. Hence when both ortho positions are blocked, then rearrangement take place at para position. I have written this here. When 2,6 positions are blocked, rearomatization is not possible in one step, because here there is no hydrogen to complete the rearomatization of this compound. Means this aromatic compound is converted to non-aromatic compound, and we know that non-aromatic compounds are less stable as compared to aromatic compound. Hence again rearrangement is going to take place, and in this case movement of this hydrogen from this place to this place produce aromatic compound. Now second rearrangement reaction of today's lecture is Cope rearrangement reaction. Cope rearrangement reaction is very similar to Claisen rearrangement reaction. The difference between these two rearrangements, in Claisen rearrangement reaction there is oxygen atom involved in rearrangement, and in Cope rearrangement all carbon atoms are there. There is no oxygen atom. Let's see here. This substrate molecule does not containing oxygen atom. All carbon atoms are there. Cope rearrangement is also 3,3 sigma-tropic rearrangement of 1,5-diene to its isomeric 1,5-diene, and that is called as Cope rearrangement. This is 1,5-diene, means double bond is present at first position, and after that another double bond is present at 5 position. That's why it is 1,5-diene. When it is heated, the movement of sigma bond as well as pi bond is taking place, and there is formation of another 1,5-diene which is isomeric with this. If there is substituent at this position, then this substrate molecule and this product, they are different. Now in this case there is no substrate molecule. That's why you can say that this compound is same as the product, but it is isomeric product. Now the movement of this pi electron, movement of this sigma electron, and formation of this bond is taking place. Breaking of this bond is also taking place. New sigma bond has 3,3 relationship with old sigma bond. Now let's see, if you term this carbon as 1, 2, 3, 1, 2, 3, there is formation of sigma bond here, and that's why it is termed as 3,3 sigma-tropic rearrangement. Now this is another example of Cope rearrangement. In this case, this is the starting compound and this is the product. Once again, there is movement of the pi bond as well as sigma bond is taking place. This is cyclobutane ring, and to this cyclobutane ring, these are two substituents attached. Movement of pi electron, movement of sigma electron, and formation of this bond is taking place. At the same time, this bond is broken, and this is the product which is obtained. We can write this product like this. Now next, Cope rearrangement reaction. This is example. It is called oxy-Cope rearrangement because OH group is the substituent which is present in the substrate molecule. The oxy-Cope rearrangement has a hydroxy group on C3 carbon atom forming aldehyde and ketone as a product. Now let's see, there is double bond, and at third position there is hydroxyl group. Once again, similar reaction is taking place. Then there is formation of 1,5-diene. This is also 1,5-diene, and in this case there is OH group present. That's why tautomerization is going to take place, and there is formation of aldehyde as a product in this case. Now this is another example, 1,2-diethyl cyclohexane 1-ol is the name of this compound. Hydroxyl group is present at third position with respect to this 1, 2, 3. There is hydroxyl group present at third position. Similarly, movement of pi bond as well as sigma bond is taking place when this substrate molecule is heated. There is formation of this intermediate product. Then this undergo tautomerization, and there is formation of ketone as the product. In earlier case, we have seen aldehyde as a product, and in this case, the ketone is obtained as a product. Now this is another example of Cope rearrangement reaction. The starting compound is 2,2-dimethylidine 1,1-bicyclopentane. 2 cyclopentane rings are there, and there are 2 exocyclic bonds which are present here. Movement of pi electron as well as sigma electron taking place when we heat this molecule. There is formation of sigma bond here, and this bond is going to break. There is generation of double bond at this place as well as at this place. Let's see here the product. This is the double bond which is generated. this is the bond which is formed, this is another double bond which is generated, and here there is no bond. That's why this bond is broken in this reaction. This is next example of Cope rearrangement reaction. 3,3-dimethyl-1,5-hexadiene. Once again, at 3 position there are 2 substituents. Similar movement of sigma as well as pi bond is taking place when this molecule is heated, and there is formation of the product. In this case, 6-methyl-1,5-heptadiene is obtained as a product. Now, third and last rearrangement of today's lecture, that is Mc-Lafferty rearrangement. This Mc-Lafferty rearrangement is observed in mass spectroscopy or mass spectrometry. Mc-Lafferty rearrangement involves migration of gamma hydrogen atom in the molecule that contain heteroatom, followed by the cleavage of alpha beta bond. Means in Mc-Lafferty rearrangement there should be gamma hydrogen atom present in the molecule. If gamma hydrogen atom is present and if that molecule containing heteroatom, then that molecule undergo Mc-Lafferty rearrangement. In this case, there is cleavage of alpha beta bond taking place. The rearrangement can occur in aldehyde, it can occur with ketone, it can occur with ester, it can occur with carboxylic acid as well as amide. Elimination of neutral molecule is taking place. The rearrangement proceeds through a sterically hindered 6-member transition state. Let's see the example. This X may be H. When it is H, it is aldehyde. When it is R, it is ketone. When it is OH, it is carboxylic acid. When it is OR, it is ester. And if it is NR2, then it is amide. Now, the carbon atom next to functional group is termed as alpha carbon atom. This is alpha carbon atom, this is beta carbon atom, and this is gamma carbon atom. If the compound containing gamma hydrogen and if the compound or the molecule containing heteroatom, then Mc-Lafferty rearrangement is possible. In this case, this is gamma hydrogen and this is the heteroatom. That's why Mc-Lafferty rearrangement is possible. Movement of this hydrogen atom from gamma carbon to oxygen is taking place. Now, after doing all this bond making and bond breaking, we get these 2 fragments as the product. This is alkene and this is another fragment. On this oxygen, it is positive charge as well as 1 dot is there. You can term is as a cation radical. This is the cation radical. When we introduce this type of molecule in mass spectrometer, there is formation of cation radical, and when cation radical undergo breakdown, there are formation of several fragments. This is the neutral fragments. This is the fragment which containing cation radical, means this fragment can undergo further decomposition and it can produce another fragment. These are the resonance of this. This positive charge can be neutralized by shifting this pi electron here. This carbon become positive charge, and this is another resonance form of this compound. Let's see another example of Mc-Lafferty rearrangement. Let's see here alpha, beta, gamma. Gamma carbon is there. At gamma carbon there is gamma hydrogen atom. Another condition for this, there should be heteroatom. Heteroatom is present, gamma hydrogen is also present, and when this type of substrate molecule or when these type of molecules are introduced in mass spectrometer, instrument of mass spectroscopy, Mc-Lafferty rearrangement taking place, movement of this hydrogen from gamma carbon to this oxygen take place, and there is formation of product. Here ethylene is formed as a small molecule, it is neutral molecule, and another fragment which is obtained, that is cation radical, positive charge as well as the radical is there, and the molecular weight of this fragment is 58. That's why m by E or m by Z, mass upon charge ratio of this molecule is 58. Means when we introduce this molecule in mass spectrometer, we get m by E or m by Z. Peak at m by E is equal to 58. At 58 we get peak, and that is due to formation of this cation radical. Ketone undergo typical Mc-Lafferty rearrangement when contain an abstractable hydrogen atom. This is the hydrogen atom that can be abstract. Now this is the example of aromatic ketone. Again, there is alpha, beta, gamma. Gamma hydrogen is present. Movement of gamma hydrogen from that gamma carbon to oxygen is taking place, and this is the fragment which is obtained. It is cation radical, positive charge is there, radical is there, and the m by E, m by Z value of this is 120 if Ar is equal to pH, and this is the isomeric structure of this ketone. Aromatic ketone undergo the typical Mc-Lafferty rearrangement if the abstractable hydrogen atom is present. This is another example of Mc-Lafferty rearrangement. In this case, there is benzene ring, and to this benzene ring another side chain is attached. In this case also the Mc-Lafferty type of rearrangement is possible. This gamma hydrogen is abstracted at this place, and there is movement of electron. Loss of CH3, CH double bond CH2 as a neutral molecule. It produces this species as a cation radical, and its molecular weight is 92. Means when this molecule is introduced in mass spectrometer, peak appear at m by E or m by Z 92. In this case, propyl radical is lost, and there is formation of this as an intermediate at this carbon. Positive charge is there, and rearrangement is taking place, and 7-member ring is formed. It consists of positive charge. Its m by E is 91. Now in this example, aldehyde molecule is there, and I have shown how Mc-Lafferty rearrangement is taking place in this case. Gamma hydrogen atom, it is abstracted by this oxygen. Oxygen carries electron pair. This is cation radical, and movement of bond taking place. This neutral fragment is obtained. Along with that, another fragment is obtained. Now in this case, this fragment has m by E or m by Z is equal to 44. Means in mass spectrum, peak at m by E 44 appear due to the formation of this cation radical, and this is the resonance structure, or this is the canonical structure of this fragment. In case of alcohol also, this Mc-Lafferty rearrangement is possible. Abstraction of gamma hydrogen is taking place. This is cation radical, and finally you will get this as a cation radical, and its mass upon charge is 56. Means when this molecule is introduced in mass spectrometer, we get peak at 56 for formation of this cation radical or this fragment. Now in this case also, this is the compound, this is ketone, and two fragments are shown here. If cleavage of this bond means alpha carbon and carbonyl, if this bond is broken, then two fragments are obtained. C6H13 as a radical, and this another fragment CH3CO plus, it is another fragment obtained, and its molecular weight is 43. hence peak appear at 43. This is the normal reaction. It is not Mc-Lafferty. But when this hydrogen atom which is present at gamma carbon is abstracted, there is formation of this cation radical or this fragment, and its molecular weight is 58, and this is due to the Mc-Lafferty rearrangement. Let us see, in this case it is shown how that Mc-Lafferty rearrangement is taking place in this reaction. Now at the end of this session we are going to solve some reaction, or we are going to predict the product during this. This is the first reaction. The substrate molecule is shown, and the question is asked which product is going to form in this reaction. In this case, name of the reaction is already given here. That's why this is the Claisen rearrangement. But if name is not given, then we have to decide whether it is Claisen rearrangement or any other type of rearrangement. Now let's see how this problem can be solved. There is movement of bonds is going to take place. This bond is shifted here, this bond is shifted here, and another shifting is here. Means there is formation of this as a single bond or sigma bond, and this bond is going to break. There is formation of carbon oxygen double bond. Hence this is the product which is obtained in this reaction. Let's see, if you do this bond breaking and bond making, then this product is obtained. Hence product of this reaction is this. Now another reaction. In this case, this is substrate molecule or starting compound, and on arrow heat is shown, means this molecule is heated. We have to decide whether it is Cope rearrangement, whether it is Claisen rearrangement, and after that we have to predict the product of this reaction. As we know that this is containing oxygen and it is allyl vinyl ether, that's why it is Claisen rearrangement reaction. Let's see how this rearrangement is taking place. Movement of this pi electron from this place to this place. This pi bond is shifted here. This sigma bond is broken. There is formation of carbon oxygen double bond. Hence it is the product which is obtained in this reaction, and it is Claisen rearrangement. Now let's see Cope rearrangement. This is the starting compound and it is asked write down the product. First of all, ignore all these things. All these things we have to find out. First of all, we have to decide which type of reaction is there. It is Claisen or Cope. There is no oxygen, that's why it is Cope rearrangement reaction, and mechanism or movement of pi bond as well as sigma bond is similar in Claisen as well as in Cope rearrangement. That's why this pi electron can be shifted here, means there is formation of carbon-carbon sigma bond here. This double bond is converted to single bond, and this single bond is converted to double bond. This bonding pair of electron is shifted here, that's why there is breaking of this bond, and hence it is shown here how that bond movement is taking place. This bond is shifted here, this bond is broken, this bond is formed, and finally this is the product which is obtained in this reaction. Dear student, during today's session we have discussed Claisen rearrangement, we have discussed Cope rearrangement, and finally we have discussed Mc-Lafferty rearrangement. Based on today's lecture, you have to solve this question and send them to my Google Classroom. First question is, explain electrolytic rearrangement in detail. We have discussed what is electrolytic rearrangement. You have to answer this question. Second, explain Claisen rearrangement with example and mechanism. We have taken several examples of Claisen rearrangement. Then third question is explain the mechanism of Cope rearrangement with example. And last question, what is Mc-Lafferty rearrangement? Explain Mc-Lafferty rearrangement observed in ketone or ester. These are the assignment. You have to solve all these questions and you have to send it on my Google Classroom. Now, summary of today's lecture. In today's lecture, we have seen electrocyclic rearrangement reaction. There is simultaneously bond making and bond formation process in electrocyclic rearrangement. Sigma bond is converted to pi bond or pi bond is converted to sigma bond. That is happen in electrocyclic rearrangement. We have seen Claisen rearrangement, we have seen Cope rearrangement, and we have seen Mc-Lafferty rearrangement in detail. We have seen the mechanism of all these three rearrangement reaction. We have explained all these rearrangement reaction with several examples, and we have seen some application of Claisen rearrangement as well as Cope rearrangement, and we have seen the application of Mc-Lafferty rearrangement in mass spectroscopy. Thank you.